Hi, everyone. Good afternoon. Thank you again for coming to one of our most recent NASA Google Talks. We do these monthly, so it's good to see some familiar faces coming back again and again. Today we have something really special. Dr. George Nelson is here from the International Space Station Project. This is a live stream of the space station as we're looking at it right now. Originally from Maine, Dr. Nelson's affiliation with NASA began in 1998 as a graduate student research fellow. He began full-time NASA career in 2001 in the training flight controllers and astronauts on the electrical and thermal systems of the ISS. After serving as the configuration manager for the space station through much of its assembly, he began its current tenure as manager of the Space Station Technology Demonstration Office, through which all of the engineering and technology research is conducted on the space station. He's based in Houston currently, and without further ado, Dr. George Nelson.
Thanks. Hi, thanks for coming, guys. As she said, this is a live view from ISS. It's from a payload, which is our term for an experiment or an investigation on ISS called HDEV, for high definition Earth viewing. And we're looking aft, and you can see a couple of Russian transport vehicles, the Canada arm that's there, as well as just a tiny bit of the U.S. segment there. We're flying over the Pacific, and I had a tracker up here. We're flying over the Pacific, and I think we're headed south by now. And we're headed south. We're pretty close to the Hawaiian Islands, and we won't really see any land probably until we cross maybe southern Patagonia in a while. But because of the way we got this set up, I'm gonna take this down and throw up some slides there for you. And this is available anytime you guys want to look at it. We stream it 24 hours a day. When you're at night, you don't really see very much. We have the cameras not tuned to pick up city lights, or we can't see any stars or anything. But we had this specifically to test out some sensors for different commercial off-the-shelf cameras. So there's 4 different cameras. There's 2 looking aft, 1 looking forward, and 1 looking down and a little bit to starboard. So they rotate through, and we take a look, and they've held up a lot better than we really thought they would. There's a couple of CMOS and a couple of CCD sensors on there. And the radiation environment is not very nice there, so we didn't expect it to last too long, but they've been doing okay. We don't really even see any pixel degradation as of yet. So if you go to ustream.tv and search for HDEV, that's where you can find this feed anytime you want it. All right. Okay. So when Terry Fong and Chris Preventer asked me what's the title of your talk, I thought, oh, I got to come up with a title. I guess I should find one that really grabs people, something of some interest. And I thought that maybe how to travel through time with the ISS. But then I realized, maybe I need to ground it a little better in reality. Although for the relativistic time guys out there, I got something for you a little bit later. And then there's a lot of things you can do on ISS, but trying to identify bubbles in commodities or other stock markets, no one has yet proposed that that's something that you really can do. So I ended up going with how best to use your neighborhood space station. And I came to that by saying that there's a lot of ideas on how to best use it, and we're talking philosophy, we're talking specific experiments, how to fund everything that we're doing. And the fact that it really is yours. So the whole thing was built with taxpayer dollars, whether you're from the United States or you're from a European ESA country or Canada or Japan or Russia. It was all built with taxpayer dollars. So it really is yours. And the way that the United States has it set up is that you even have direct access to it through a mechanism that I'll explain a little bit later for you. But it's open to United States corporate and private entities to help the tax base of the United States. If you got a great idea and you're going to end up making money on the ground after proving something out on ISS, and you're going to hire Americans who pay taxes and make the world better, we're there for you, and we hope you get to use it. And then being a neighborhood space station, when you look at the cosmos overall, it is definitely in our neighborhood, and really it's only a couple hundred miles up. So it's pretty close by. We provide you access for it, and if you guys provide the things to do on it, well then that's one of the best ways you can use your neighborhood space station. So The vehicle itself that you just saw, that's about the same location, a little bit further south as we are right now. This was yesterday morning. It passed over. You can see, if you've ever compared it to a shuttle flight before we started building ISS, this goes to much higher latitudes than the shuttle normally did. And that's because we wanted to have access from our Russian partners who launch out of Kazakhstan. And then they try and launch over the top of China rather than, or rather north of China rather than directly over the top of them. So that's the inclination that we have, and so that sets up the angle that you see the orbital track takes to the equator. Okay, so I want to talk a little bit about what it took to build the space station so that you guys understand the challenges that NASA and the program itself have been trying to tackle in properly using it. So I think the Russian number is actually from July, so I think you can say that that's either 98 or 99 now, total Russian launches. Most of those have been unmanned Progress, which is the resupply vehicle from the Russian Space Agency, or the Soyuz spacecraft that can take up and down 3 astronauts or cosmonauts. And that's also the primary lifeboat, the only lifeboat that we have for the ISS in an emergency to get back home. 37 Space Shuttle launches. So you look at it and you think about how many we had, that's about a fourth of all the Space Shuttle launches that we did was for ISS. It was the real workhorse. It was the original intent of the space station. The Space Shuttle program was to build a space station. Had a big payload bay to bring up all the parts. We flew the Japanese module that the Japanese built. We flew the European module that the Europeans built. We flew 2 modules that the Europeans built for us in exchange for flying their module, and a huge American segment as well. We've flown some commercial vehicles as of late there as well. You know Elon's effort through SpaceX, and Orbital Sciences is also flying commercial vehicles to ISS, unmanned, and in a resupply fashion for all the utilization, all the experiments that we try and conduct there. The Japanese have flown 4 HTVs, and the Europeans have flown 5 ATVs. Those are also both unmanned. The difference between the two, Europe launches from down near the equator off of South America. Japan launches from an island called Tanegashima. The ATV uses a Russian system to dock autonomously in the same way that their Progress docks to the station. And the HTV rendezvous with the vehicle, and then we grab it with that Canada arm that you saw and berth it to the forward end of the vehicle. So I talk about all this to say this was, the very first Russian launch was back in November of '98. Is that right, Chris? November of '98 was when the Russians first launched the FGB. Now this was a section that the United States largely compensated Russia to build. And then with the Space Shuttle, we went up and attached our Node 1 to it. And then we waited for quite a while until the Russians were able to build their service module. And then it was a habitable platform. And since then, we've had continuous human presence on ISS. So that's been since 2000. I think also at the very end of 2000, we've had continuous human presence up there. And the amount of effort and time that it took just to build the space station, you can imagine that that was the focus, get it built. And then especially when we put a sunset clause on the Space Shuttle program itself, there was even more urgency. Let's get it built, let's get this done first. So that was the primary focus. But now that it's built, using it is the most important thing. So anytime that you spend that much money and that much time, you're going to have a considerable amount of inertia that you have to overcome. And then you complicate it with the fact that it's a government project, and you have even more. So it's been challenging to do the change that was required. But what we did, as soon as the Space Shuttle program ended and we had fully utilized its capability to get us ready to be without it, we reorganized a large part of the space station program in order to more properly reflect the priorities that we now have, which is doing the science and engineering research on board. So prior to that day, the Payload's office had largely its own they were self-contained. They had their own engineering support. They were like their own little program because they were just off on the side. And Chris was with me doing a lot of the training that we would do, and in any simulation that we would run, as soon as a major malfunction would happen, was the first thing that happens, turn off the payloads. And so that kind of ingrains into the flight controllers and everybody who's getting trained at that point that, look, that is not the important thing. The important thing is making sure that the facility is still running, everything is okay, the crew is safe. We still care about those things, but the primary focus now has to be on getting the science done. So one of the things we did is we got rid of the separate program aspect of all the science they were doing, disseminated those individuals throughout the program. There was some optics type thing, and I don't mean optics the discipline, I mean optics just how things look by moving the program scientist on the org chart up next to the program manager. The mail code for payloads is OZ. So historically, we've been at the bottom right-hand corner of every org chart. That's moved up as well, and we're still working to make it better because we've had more than one accident where we have loss of life, right? So we have several decades of work building up processes that ensure safety. But when you're trying to do scientific research, you don't need to necessarily focus on mission success. Well, you need to focus on the particular aspect of what you're trying to discover. So all the rigor and extra money and cost that goes with building a typical spaceflight project, we don't want to incur those costs in order to do research and to use the space station like the lab next door. And so I tell everybody, you got to treat it like it's a facility down the road, and I'm paying for your transportation costs. I take care of the flight up. We take care of the crew being there. We take care of the power and the thermal and the data, all the stuff that you need. All you got to do is build it so that it works for you, not for us. So we're still working to fix our processes so that you and even other people within our own agency have better access to using the facility. And one of the things that we did was we set up 3 offices. So there was the National Lab Office, and so that's what I alluded to before. So anybody outside of NASA, whether it's another government agency or a private company or a public company or an individual who has a good use for the space station platform, can go through the National Lab Office, and we hired a not-for-profit entity called CASIS, the Center for Advancement of Science in Space. And one of the reasons we want to do it is we trust ourselves to choose the right investments that NASA cares about for space flight and space exploration and aerosciences and the like. But we didn't want 20 years from now someone saying, we could have cured this disease if you guys had only let us fly on the ISS. So we have this not-for-profit entity that hires the right experts in all the different fields where we're getting proposals to properly vet and evaluate and prioritize the different things that are being proposed to fly on ISS. So that's one way you can get up there, through the National Lab Office. The second office that was created was where I work, the Technology Demonstration Office. So we have all the engineering and technology research that gets done on ISS flies through this office, as well as all the Department of Defense work. So that's kind of like the caveat, the exception that proves the rule for the National Lab Office. That's supposed to be all the external to NASA government agencies. But there's a peaceful purposes clause for ISS, and so all the work the DoD does is peaceful work, and so that's directly in line with all of NASA's needs. So for accounting and stuff, we keep the DoD stuff as part of a national lab utilization, but in practice it all flows through us. And the third office that we came up with was the Science Research Office. So there's this whole section of the agency called the Science Mission Directorate, and so these are the guys that fund the rovers on Mars and the Hubble and the Webb Space Telescope, and do a lot of great stuff, but they have their own bureaucracy, their own vetting of what they want to do, and all of their work and all the work that they fund outside the agency as well flows through that particular office. So one of the first things we did was set up those 3 front doors. Let's see. Part of the change that I said was challenging was reminding everybody who the customer is. So when you work in a government agency, while you work for the citizens of the country, you often consider yourself to be the customer. You're working for the people, but the contractor who's supplying you with something, they need to understand you're the customer. But now we're completely different. When we're running the space station, we're not the customer anymore. The customer are the principal investigators across the country, and the world in our case, that are trying to do work there. So reminding everybody of that, and reminding people that this is not the last space program, or the one before that even, where you have a mentality that worked very well for us of, failure is not an option. But in this case, it's a very difficult way to run a research program. If you look at some of the more aggressive research programs like that DARPA runs, failure is almost a necessity. If they are too successful in the portfolio that they're investing in, people get a talking to, like, I don't think you're taking enough risks. So the risks that we want everybody to accept with using ISS are not safety risks. We're not asking to put the crew or the vehicle at risk, but making bold steps and taking risks technically to see if we can come up with the best solutions is exactly something that we want to encourage. So while we've become this customer service organization and we continue to help everybody figure that out, we've tried to help change the attitudes just with everybody that we work with every day. So a standard conversation would be, as you're walking across in between buildings at Johnson Space Center, would be, did you hear about effort X? They needed 3 times to get that done. Can you believe, why couldn't they get that tested on the ground? Why couldn't they figure that out? And that's exactly the type of attitude that we're trying to change a little bit, where it's okay to have iterative tasks on orbit. We have a crew there for a reason. You can build something and fly it, and if it didn't work the way it was supposed to, well, how many times have you been in a lab and it worked the first time, every time? And that's really expensive if that's the way you want to operate. So we're trying to get people to accept that this is a lab and it doesn't necessarily work the first time every time. And when you discover how it goes wrong, that's the benefit of using the lab. So what kind of things can you do up there? I'm talking about all these things that you should and could do. What kind of things can you do there? Well, let's look at a few things that we're already doing up there, and kind of split it down the middle between non-NASA and NASA. So there's biology and biotechnology investigations that are up there that are on both sides. Most of the human research has been funded by NASA. There's not a lot of commercial need identified yet with people spending money, or their own money, on trying to figure out the human effects. And it's of great importance for NASA if we're going to take long duration missions to Mars, for example. The physical sciences are funded both by NASA and by other government agencies. Technology demonstrations, that's one of the things that I spend a lot of time harping on other entities about, is the fact that this is a lab that can be used. It's really difficult within the aerospace community to change the paradigm that most executives in most aerospace companies are used to. That paradigm is, we'd love to do something for you, NASA, and we'd love you to pay us to do it. So I'm trying to get to the point where they're investing their own money and keeping their intellectual property and utilizing this national asset at the same time. So it's a tough thing to convince people of, because the performance period cycle of that particular vice president is probably shorter than the return on investment for whatever they're going to fly to ISS and test out, and then when we finally decide that we're going to go back to the moon or to Mars one day, we buy that one because it did so well on ISS, right? So that VP is long gone by the time his company gets that ROI, and so it's getting to the right level of the different companies and the different corporations and getting them to accept this possibility has been a challenge. We're getting there, and I think you'll see some things coming up soon. What else? Astrophysics, NASA, that's kind of NASA's mandate, right? So we fund the astrophysics work that gets done up there. Earth science, there's a lot of different things, both funded by NASA and not. And we'll talk a couple examples about that later. And then on the education side, you guys work for one of the entities that does an awful lot of work in that area, and NASA tries to use the assets that we have to do the same sort of thing. So some of the You may have seen some videos or pictures of the astronauts working inside the station. As an exposure facility, we have a lot of options on ISS. And outside the vehicle, we have 4 logistics carriers, 1, 2, 3, 4. They're on the main truss that goes across. That was all part of the United States contribution. And on those, we have some spare parts that we flew up there that were so big that we knew we needed to fly them up on the Space Shuttle first. So we have those pre-positioned when we have to remove and replace the originals. But we have a lot of payload spots on there. So some of the different things that you can do up there is look up or look down or take material testing in that environment. There's a lot of atomic oxygen there. There's, as I said before, the radiation environment. If you want to do other things in this area, you need to make sure that your materials are going to respond over periods of time and respond well. Both the Japanese and the Europeans have exposed facilities that they have the opportunity to put stuff on. The United States has access to both of those facilities as well. And then we have some specific areas that we've placed different investigations, like the AMS is not on an ELC, but it's out there on the truss, and we'll talk about that a little bit later too. And the Russians have their own investigative program as well. By far, it seems the United States and its partners have invested more so far in the research side of ISS. So, why would we take all this time and money to do this sort of thing? Well, it's the concept that nations explore in order to advance, and the exploration can come from physically going somewhere to explore, or just further observation of either natural phenomenon or things that you can observe. And that exploration drives technology breakthroughs and scientific discoveries. And without that exploration, that cycle of improvement can be broken. But the ISS partnership, in the fact that it really spans the globe, has transformed the space exploration from an effort for the advancement of individual nations like Russia and the United States in the 60s, and China right now, to an endeavor to, it's committed to the advancement of humankind. And I read that directly because it's a pretty heady statement, right? Get a hold of yourself. But the reason it's justified is the fact that we have, just as of last year, almost 70 countries who've managed to participate in ISS using it. Not just the partnership countries. So you can see the 4 main partners at the top of that ring: the United States, Canada, Japan, and Russia. And then the rest of the ESA represented countries in the rest of the flags, and then all the other participants that I mentioned on the side. So we've gotten a lot of use of the ISS so far across the world, and it can have a significantly stabilizing effect beyond just individual principal investigators from different countries collaborating. So carrying on with the humans explore concept. So they explore in order to advance. So you can debate all you want about Columbus's initial intentions or final intentions, but it's hard to debate with against or about the influence that his initial trip had on Spain and the subsequent trips that continued. They didn't go once and stop. They went and continued to go, and Spain, significantly left the Iberian Peninsula, and at one point claimed nearly half the world. In contrast, in the I think it was the 1400s, the Ming Dynasty had sent out a large naval fleet that was larger than anything the Portuguese were sailing through the Indian Ocean. And then when that monarch died and his son took over, he pulled back and they stopped the naval exploration. And there's one train of thought that says that helped lead to the Ming Dynasty's end, was their lack of continued exploration, and they weren't there when the Portuguese came in with much smaller boats. And like I said, you can observe from where you are, or you can go there to observe natural phenomenon. If you look far enough, you can see some interesting things, like and gain something from it. So you have Isaac Newton proving everything that he was looking at by observing the curvature of a comet, and that led to calculus and proving that. And a lot of the missions that actually went somewhere to explore, the standard way to do that was to bring a naturalist with you, a scientist or a naturalist. So we have Captain Cook, and it shows the resolution there. I think his first trip was on the Endeavour, and that was to Tahiti to observe the transit of Venus. And so the big thing there was trying to discover or to prove the size of the solar system. And the problem is that science takes a lot of time. So they got back from that trip, and the Royal Society that had funded them, based on the recommendation of Halley several decades before, were completely unimpressed with the data that they brought back. This is no good at all. But it turns out that later on, when they were able to double check a lot of the work in the next transit, they were able to say that they were within less than 0.5% accuracy for the size of the solar system. So science takes longer than the exploration itself. In subsequent trips, he was looking for a Northwest Passage and found Hawaii. I think that's a good return on investment there. On Darwin's trip, this was a trip, the trip of the Beagle, the second one, the one that Darwin was on. He was observing a lot of geology stuff, and that was a trip that was specific to map the west coast of South America. So it was a strict exploration mission to bring back cartography, map out the west coast. But Darwin noticed seashells at altitude when he was ashore, and then noticed a lot of the other natural stuff. And it wasn't until 20 years later that Origins of Species was actually published. So my point in all this is that science takes longer period of time than the specific exploration that you're conducting. So some of the things that we're doing up there. Biology, whether it's an animal cell or whether it's a bacteria, we're recognizing that, particularly in things like gene expression, that the microgravity environment ends up stressing the organism. And that stressing of the organism ends up expressing itself in genes. For the same way it does in a large organism, if you stress it a certain way, certain things come out. We're recognizing the same thing in observations on ISS. And yeah, go ahead.
What's the radiation environment inside the station? Does that also affect the expression?
It can, yeah. And I think the one that sticks in my mind was that Shannon Lucid did some work on Mir before we had ISS that showed higher rates of mutation on things. But they try and back that out and make sure that what they're looking at is this. And the important thing is not necessarily that, it's microgravity that turned this particular expression on. It's recognizing that when that gene is turned on, this happens, so that you can then go ahead and prevent that or encourage that in order to do what you need to do on the ground. But the ISS is considered a radiation environment, and the crew are considered radiation workers. So we do a lot of work on monitoring the radiation environment, and I'll mention that again in a little bit later when we talk about some of the technology stuff that we're trying to do. Is that enough? Okay. Okay. So other biology stuff, just larger scale systems, right? So plants, it'd be nice if we could be able to grow plants on a transit mission. So these are some of the things that we're looking at, but there's also fundamental research involved with some of the work that we're doing with plants up there. Human physiology, there's plenty that goes on with the human body when we're up there, and some of them that we managed to even start to overcome. So we've had a long time. You've probably heard about crew coming back after a long duration mission, basically with osteoporosis, right? So as soon as you get up there, you stop stressing, particularly your large bones in your legs and your back and your hips, because you're no longer loading it every step of every day. And your body's very efficient, and it just starts flushing everything out. To the point that was beyond what we even thought of when we built the environmental control and life support system for urine processing. It fouled nearly immediately when it got up there because it wasn't built to handle the large amounts of calcium that the crew was dumping out every day. But through the right ratios of protein and potassium, we think we've and serious amounts of time exercising, we think we've overcome most of those issues for the crew. And we'll see whether that ends up helping my grandmother or somebody else's grandmother later on. And that's one of the ways that it actually does transition into an Earth benefit when we research these type of things. Plenty of physical sciences work that's up there. So I didn't make this particular slide, and this one often turns, and to me it was a little hokey, but you guys all understand there's no convection in space, right? Because there's no gravity, right? But the thing that I didn't even realize until a couple years ago is that we don't have any data on, for instance, large-scale combustion. And we've done a lot of work on flames in space, but it's all been very small, very contained. And so we're going to do some large-scale fire tests using ISS. And when I first heard of it, I thought we're going to do some big Wrath of Khan, like glowing orb that is going to burn up out of the sky. This is going to be the coolest looking thing. It's not going to be that cool looking. But so what we're going to do is we're going to take the orbital Cygnus vehicle. That is a vehicle that normally burns up when it returns. So we have 2 commercial cargo vehicles that I mentioned from the United States. SpaceX has a heat shield and is recoverable, and we bring back science to do analysis on the ground. The orbital vehicle right now is designed to burn up, so we put garbage and other things that we want to get rid of into that vehicle, and it hits the atmosphere at the right angle so it burns up. But we're going to take a large part of the inside of that vehicle. I thought we were going to set the whole thing on fire when the proposal came to me. But they're going to do it multiple times on multiple return missions of the orbital Cygnus, and we're going to get data from it. And it's just going to be a large box on the inside that's burning within the box. So it'll still be a controlled reentry. Everything will be fine, and it'll be far less like the movies. But it's still going to be very interesting data for that. Astrophysics and fundamental physics. So way out of my league with this type of stuff. But so we got a guy named Sam Ting who's got a Nobel Prize at home who came up with this particular effort. He realized that this was the only way he was going to get this particular research done. He's looking at dark matter. We got a special spot right for him. He ended up redesigning everything to have a permanent magnet instead of electromagnet. This has been the work of thousands of people just for this one particular experiment. And we'll see if he doubles up on his prizes by the time he gets all this data together and gets all his publications out. And this is the type of stuff that he's looking at. I'm not sure, this doesn't have the info on the number of hits. So the number of data samples that they announced that they've had through AMS is almost getting silly now. I think it's, I can't remember to which power it is, but it's at least 10 to the 20th number of hits and particles that they're taking. And so there's vast number crunching that goes on with trying to decide what they can infer from all this data that they're getting. And so most of that is to come. Okay, well, so now more into the area that I am. I'm an engineer, so most of the stuff that I have a little bit better understanding for is in the area of technology and engineering. So we do some stuff up there with that. We got the Robonaut project manager right here, and Ron Diffler, and that's one of the things that we've done up there. And there's a lot that we have to figure out if we're going to go somewhere else. So we got the ISS there now, and it's state of the art, right? There's really no better space vehicle that's flying anywhere, regardless of the fact that we got older laptops, and we've got computers that we call MDMs that are running. What are they running? Yeah, 286s or something. I mean, so they're very reliable, they're rad hardened, and they do very well. But it's the state-of-the-art system, and it's built specifically, the whole vehicle is built to be where it is in low Earth orbit, where we can launch a Soyuz or maybe later on a commercial crew vehicle or something else and get there very quickly. Or in a real emergency, the crew can come home, no problem, very quickly in the Soyuz. But if we're going to go for a long time a long distance away, there are other things that we want to do. And we want to use the space station to prove out all of the technology that we need for that. We don't want to find out halfway to Mars the urine processor doesn't work. That's not so great. So we tried to come up with, all right, so what things do we want to do up there? And obviously, any engineer in this room could probably come up with most of the general areas that we needed to do. Figure out your environment. Get your reliability where it needs to be. Look at the logistics that you do or don't need for the mission that you're potentially going to do, and reduce that risk implementing it somewhere else. So we came up with a bunch of areas, and we used the National Academy of Sciences, the National Research Council, the agency does, to tell us what to do a lot. On the science side, they have something called the Decadal Survey, and that's like their Bible. If it's not in the Decadal Survey, you're not going to see the Science Mission Director spending money on it. On the tech side, we also get inputs from the National Academy, and the underlined ones are the ones that they had recommended that we focus on. But sometimes, or the underlying ones are the specific experiments that address areas that we were told to concentrate on. But a lot of them don't necessarily complete the problem. They don't put to bed the problem. So we started throughout with all our partners. We got these teams together and we said, okay, we're going to figure out and prioritize what we're going to use ISS for technology demonstrations. And we all sat down and we came up with all the areas that we thought we were going to come up with in the first place. And we did prioritize ECLSS, the Environmental Control and Life Support Systems, as the top one. So we have a lot of consumables that we end up using with the ISS version of ECLSS. We end up relying upon a logistics train, the resupply vehicles that we have for that ECLSS. There's things that we need to do in order to go to Mars, for instance, with ECLSS, and we can identify those. So that was good. And then on the radiation side of things, we said, we need to figure this out too, because it's a different radiation environment once you get outside the Van Allen belts, and we got to know all about that. And so when we looked at it, we had a million options on what to do for environmental control and life support systems. And all of us were well-rounded generalists in the areas of space technology. And we didn't think it was really fair for the 6 or 7 of us that were tasked on this team to make these large decisions. On top of that, it's a political environment that you have, right? So you have one idea that comes from Alabama, you get another one that comes from Ohio, you get another one that comes from Texas, and no matter which one you choose, somebody says, well, the reason they chose that is because of this. And then somebody calls an elected official, and then all of a sudden you're designing your spacecraft inside the Beltway instead of where it needs to be, on a drafting table, or the modern equivalent of it. So what we did is we said, all right, we're going to set up teams, and we're going to use them the exact same way that the rest of the agency uses the NRC and the national academies, and tell us what's going on. Because while on the ECLSS side we had a million options, on the radiation side we had a real lack of options. We sense the heck out of radiation up there, and that's what all the proposals were: sensing, 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 sensing. So we're going to be able to tell a crew, you're smoked. But I'm not sure how we can tell them that, but you'll be okay. So that's one of the things that we've tasked that particular team with, and we've called them system maturation teams. And we've set one up for ECLSS, we've set one up for Common Nav, we set one up for radiation, we set one up. We already really had a program for the human research program really already existed before this. So we said, hey, you guys make sure you concentrate on that. So we did that for all the technical areas so that we could properly identify, and we told them, we just want you to evaluate the technical solutions. First identify the technical gaps, and then help us identify the solutions. And we're trying to take any politics out of it as to whose idea. So we have experts from across the agency. We populated it from every center, and when they come to a consensus, we've got it so the technology investment teams within the agency and the programs can say, well, what does the SMT think about this? And they say, oh, they think this is their top priority. And that's how we get things funded and flown and executed. And it's important because if you've paid attention to any federal budget discussion over the last few years, it's a zero-sum game, right? So if we end up choosing the wrong thing to invest in and it costs X dollars, those dollars are gone, right? And it can't be used to spend on something else. So when we look at the technical gaps that we have to agree that they're general enough that they should be addressed now before Congress or a president tells us this is your mission. Because everything that we're doing now is based on a generality. We know we want to go out there somewhere. So we look at all the generic solutions to these technology problems and prioritize filling in those gaps based on what you need, the lead time in order to develop them. If you know you need 4 years on an ECLSS system, well, you better make sure you have 4 years left of ISS by the time you fly it in order to vet it out and then make any mods that you need to once you're there. And we're trying to get the teams to develop, and some of them have already, specific roadmaps so that we can then say, you know what, we're done with the space station. We've met every goal, check, 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 and we can hand it over to commercial entities, or we can simply let's transition to deep space because we've managed to address what we need to using this vehicle. An important thing to understand is that people look at things differently depending on who you are, and it actually is missing. There we go. Okay, so depending on who you are, you might look at the flow of how the space station got up there a little differently. If you were building it, if you were part of the project management, you'd design it, and then you'd assemble it, and then you start using it, and then you think about, okay, do we need to use it for a longer period of time, or are we good? Then you look worry about extension. If you're on the science side, well, in the design, yeah, people are telling me that there's going to be a space station. Let's hold off and see if one actually gets built. And then we start building it, and they're like, all right, well, let's wait until it finishes. And then, okay, you guys are really done? Okay, go right ahead. And we really saw that. We saw this gap. After we were finished building it, we turned around and said, who wants to use it? And there hadn't been this backlog of science waiting to use the ISS, because that's not the way that you get your research funded, is by saying, I'm going to go do some research. I'd like you to give me several $1 million, and I'm going to conduct it on that vehicle that doesn't yet exist. So we had to wait. First, we had to promise that it got up there. Then we had to deliver it. And now we're seeing a lot more usage and requests for use now that it's been there and it's a proven commodity. And then if you're just in the organization, first you worried about all the requirements and how to get the things done. Then you worried about building the vehicle and getting the crew there. And this is the transition that I was talking about before, this changing your focus to research. And then, okay, are we going to continue that or not? And then this kind of just mentions the things that I've already talked about with operating safely. It's probably not enough. You need to take enough of a risk so that you get the proper return on the investment. And it's what I was talking about before, that it's a real laboratory, and it's okay if things don't work the first time. And getting people to accept the fact that that's perfectly acceptable. Okay, so I mentioned some earth science stuff before and said that I would talk about it. So it turns out it's a really great platform. So I mentioned that we are at a higher inclination than a lot of space shuttle flights would take. So we would launch out of Florida, and so you would, from that latitude, you would get to a higher altitude by staying at that latitude instead of going to a higher one. And that's probably where ISS would have been if it was just Space Station Freedom, a sole United States effort. But because we wanted to have access by our partners to the vehicle, we're at a higher inclination, which ends up providing a lot more access and a lot more visibility to the ground that we wouldn't have had otherwise. So you end up covering 85% of the Earth's surface flying over it, where you wouldn't have. You'd have been kind of skinny down no further north than Florida. And then every 1 to 3 days, you end up passing over 95% of the world's population. So not only is it an international space station because of investment, but it's international in that if you go to your computer and you look up ISS sightings, you can see it go right over your head often. And it can make observations of where you live, which can be significant as well. Some of those observations can be in the hyperspectral zone. So this is looking at a lot of stuff, whether it be ocean temperatures or reactions of the ocean to changing temperatures, or it could be we've had agriculture requests to look at things like the Napa Valley for the way that agriculture is responding or not to climate. I mentioned the relativistic aspect of it. So in 2016, the ESA is going to fly the ASIS. So this is an atomic clock. It's going to have 2 clocks in it, actually. One is going to be based on cesium atoms, I think. I can't remember what the other side is. But between the 2 clocks, they'll have an accuracy of better than 1 second for 300 million years, right? And so they're going to compare that to very accurate clocks on the ground and compare and end up proving out some Einstein stuff, or maybe proving it to be debatable, but between gravitation and relativistic time. So even before we said, hey, everybody, it's open for use, open for business, come and use it, we'd already done some significant things really in the spare time. We were spending a lot of time building it, but in the spare time, we still managed to do quite a lot of stuff. MAXI was a joint venture with JAXA and us, and so they were able to observe and complement another observation of a black hole swallowing a star. This is the first time that had been done. They noticed something with the crew, that there were certain crew members, they were coming back with vision issues. So they realized that it might be, it's environmental for sure, but it might affect specific crew members more than others. So we've been looking at that, and whether it's intracranial pressure or whether it's a gene expression type thing. Microbial virulence, so that's what I mentioned before about the stressor on everything, not just cells, but microbes as well. And so there's some, resulting from that, there's some candidate vaccines for different things that have been out there. And I removed the slide from it, but there's that valley of death for technologies and science research that comes out, right? So there's this rush up with results that end up being obtained from all this work, and then getting across that final valley to whether it be something that you can do a human research trial on, or whether it's a true commercial product or anything. You got to get across that big hurdle. So you can hear a lot of stuff that gets to the point that I'm talking about right there that never gets into a hospital or into Best Buy or somewhere like that. Let's see. The NASA exploration mission side, that's largely what we're tasking the SMTs to help us come up with the proper investments to do, and they're well on their way to doing that. We've had some spin-offs in technology area, like robotic assist for brain surgery. There's a need for telemedicine when it comes to having a crew being that far away from Earth. There's filtering for air that has come out. You need the crew to breathe the same air all the time, and it's got to be compatible with human life. And then, let's see, the last one, remotely guided ultrasound for maternal care, another telemedicine application. So my original question or title was how best to use. So here's some final points on how I would best use it and my recommendations for it. So prioritize your resources of limited life. So the saying that a lot of people in the NASA area have heard me use a lot was use the space station now. The ground's going to be here forever. So there's a premise that you can't fly something until you're ready to fly, because I can't be that guy that people are talking about that it didn't work the first time. We flew a carbon dioxide removal solution called a mean swing bed, which was going to be applicable to the next Orion vehicle that we're building. And we built it, by NASA standards, we built it on the cheap. And it flew up there, and it didn't work. And we ended up using the crew to fix it. And it wasn't a small amount. It wasn't a small amount of time that we ended up doing, and we considered bringing it home, which was also another acceptable solution. We've paid for the logistics, so you can fly something there. If it really doesn't work and it really can't be fixed on orbit, we'll fly it home, we'll tweak it and fly it again if it's of the right priority and the right need for either you, the country, or the agency. So prioritize the work that you're doing and fund it appropriately. You don't need to overspend, and I don't recommend underspending. Force the institutional change that's required. So we did the reorganization that we need. We're redesigning processes still every day. There's a specific team at JSC right now that is changing the entire process by which we accept experiments to ISS because we deemed it as too expensive, as did some of our customers. If you guys are providing products that are too expensive for people to use, you're going to make a change. Well, as a government agency, there's not always the same impetus, but we have enough people that care enough about this that we're doing exactly that. And then change the perceptions of your organization, how they perceive everybody who is going to be their customer. Have a plan and measure your performance to it. That might scare people who are big on fundamental research. It doesn't have to be the results that you plan for. It just needs to be planning appropriately for what you want to investigate and explore. On the tech side, we have specific goals that we need to get to. Embrace the private sector. So we're certainly doing that in the logistics train. We don't have any NASA-owned assets, and that's been something to get used to. We pay SpaceX and Orbital to get stuff there and back, and for now, we pay the Russians for humans to get there and back. So I think we're doing that, and the part that I discussed before about trying to get American entities to recognize the space station is there for them, they can keep all their intellectual property, and we assume effectively all the risk if you build the hardware. Getting that word out is important. And then getting word out is really important that people understand the benefits that we're getting. So if you have people that are properly reporting the work that they do, whether it's something as significant as origins of species or not, it's important for people to understand this was possible because of this asset, and it's good that our elected officials can understand, all right, this is something that is actually benefiting people in my district, people in this state, or just people on the Earth in general. So, increasing the public knowledge is a real thing, and even that is of benefit to everybody here. So that's all I had, and so I can open it up to questions.
So it's kind of a double-track question, but I don't hear much about the International Space Station in the media, and in parallel, we had Maria Klawe here last week talking about building inclusive environments and getting more women and minorities involved in STEM and CS. I don't in any way mean to propose doing like crass dog and pony shows with the International Space Station, but do you have an outreach effort to try to get kids of all backgrounds from all around the world excited about what the International Space Station is doing and engaged with the experiments that are happening there?
Well, very honestly, it's not something that historically NASA's done very well, just outreach in general. And I think that when you have the type of people that NASA historically has been attractive to, they're all about the mission, right? And so if you go to the moon, that's going to get people excited, right? But when you talk about science research, I think of that Big Bang episode where they're like, let's get to work, right? And they play the theme to Rocky while they stare at a whiteboard for an hour. Like that doesn't always get people excited, right? So I think one of the best outreach activities that ISS has been through YouTube and Google when they were able to get, I can't remember how many proposals they got, but they ended up selecting 2 to fly on ISS. That's not an insignificant thing, particularly for those kids that managed to do it and exposed everybody who even tried to be selected to the process of developing and proposing scientific activities. I think that's great. We recently had a 3-day, wasn't really a retreat, but we had a 3-day discussion with the ISS leadership recently. And that was one of the things that we talked about was the outreach aspect and making sure that people understand everything is really part of all of our jobs. So that's one of the reasons I'm here.
You mentioned a couple of times that the resource is limited, that it would have an end of life at some point. Could you tell me when that is, and then what is NASA considering for as it develops larger and perhaps more complex space stations?
Well, I was talking to, it's kind of a complicated answer as to what the space station life is right now because you have so many different political entities that are involved with it. So 2016 was the original date. The United States has approved 2020. Our partners are working on approving 2020, but there's general acceptance within for instance, my colleagues within the space station program from other countries, that it's 2020. The current administration has said that they are good with it being to 2024. There's a general rule. It's shocking that they follow any rules consistently, but with a general rule within the Beltway that you don't commit 2 administrations beyond you to anything. It's not law, but 2024 is kind of the general acceptance within the United States as to how long we're going to have and use the ISS. And then everybody within the program itself has been working to certify all of the hardware to make sure that the vehicle itself can last at least until 2028. So we think we have a reasonable future in being able to provide a product to customers that are out there. And it's important that people understand that horizon is well down the road, because a lot of these investments take several years to first fund and then build and then fly and then refly if they need to. So assuring people that we're going to be there for a while, I think, is an important thing to get across.
Yeah, saying 2016 would probably kill most people's
Yeah, we
consideration.
addressed that pretty early on after assembly complete, that we were going to need, in order to do what we need to do, it needed to be, minimum 2020. We got concurrence with that, and then general concurrence on, we're looking at 2024, and then the whole time, you don't get to go beyond 2024 if that is what your goal is, right? So we're trying to make sure that everything is capable of sustaining flight well beyond 2028.
So the next step for NASA is not necessarily another space station, but more along the lines of a trip to Mars. Is that what I'm hearing?
I think that is the general, you can get in trouble by saying this is what we are or aren't doing these days, but the general consensus is that all the prep work that we're doing, particularly in tech and human research, is to enable a trip to Mars. Now, whether you do that by making a pit stop at the moon, or whether you do some asteroid work first, or wherever, it doesn't seem to be offensive to anybody to say that's an eventual destination. And it happens to be really hard. So all of the tech solutions that we have are really bounded by that extreme of trying to go to Mars.
Did you have an updated take on Kessler syndrome? And is there a way that newer satellite companies like Skybox and things like that sort of change that equation?
Well, so the access of other companies is there. I don't know if you heard that part. I'm not good to be able to give you an update on any of that stuff. But the access of private entities to ISS is established, and it's a really open road to get there through CASIS, the Center for Advancement of Space Science, and those guys can help anybody get there. The law is written that half of the U.S. assets are designated a national lab. They didn't specifically tell us how we were supposed to measure that percentage, or whether it was measured on a monthly or a yearly or a 5-year basis. But we haven't really approached 50% of upmass yet on each launch. So there's plenty of room there for private companies to try and do stuff.
Yeah, just following up on the question about lifetime, what's the average proposal to flight time for projects that come into your office?
For the things that come into our office, when I said, one of the things about embracing the commercial sector, right, is we had to let those guys get off the ground, because we didn't end up starting with it wasn't Boeing and Lockheed that ended up proposing to be the commercial providers for the commercial cargo. So SpaceX had to start from the beginning. Orbital had to build their whole vehicle themselves as well. So there was a significant lag in our ability to deliver hardware for a while until they really got going. So for instance, the cameras that I showed when we first got in here, we were racing to get those built just in case another payload wasn't ready for SpaceX 3. And that was in 2011. And we didn't launch until this year to get that going. But now I think we're about to start cruising, I think, with real regular transport. So it's quite variable when you say how long does it take. Most of them are not, that's a very simple payload, 4 cameras in a box outside, make sure that it doesn't fall apart, right? So that was very easy to build. Most of them are not waiting for a ride. But for instance, the legs that went on Robonaut, those waited for a while. And that particular project needed to figure out their funding profile as they weren't integrated at ISS. And so that falls into part of my responsibility when we prioritize the work that gets done, not just the upmass, but what the crew spends time on. And that's part of the discussion when I say, no, this has to be the top priority because that researcher is losing funding at the end of this quarter. So that's why it's the priority. And so loss of science is a huge driver in getting things done at ISS. It's one of the reasons that the human research program gets so much time, because if you go through 5 months of a crew member on orbit, and you need the 6th month in order to complete the run, it's complete loss of science. This guy's coming home. You can't do anything else after that, so that becomes a priority in one of the discussions. But we can get stuff, the standard template is 18 months. 18 months from when you get effectively manifested for that increment, for that period of time, and then fly. You got to be on dock. It depends on the launch provider, but you got to be on dock usually 90 days ahead of launch.
So it seems like cost is the primary limiting factor on the lifespan of the ISS?
I'm not sure that's true. I mean, it has to, so whose cost? So cost is a significant factor in the investment of the science that gets done. Way back when the space station was conceived, there were going to be 2 pots of money. One to build and operate the vehicle, and a second pot to do all the research. Well, long ago, that second pot failed to exist. And so we're in a situation of build it and they will come, and part of that is getting the word out. So there is a nominal amount of NASA's budget that is required in order to continue flying the ISS. So that would be required if it was going to continue to be a government asset. It's possible when NASA has met all of its needs that it gets turned over to a corporate entity that manages to continue to use it. Depending on when that is, it might be the hardware that is that's the limiting factor on continuing to use it.
And are the costs going down as companies like SpaceX reduce cost to launch?
Well, I mean, we only have one contract so far for commercial cargo. We were talking earlier that we're going to talk. I think there's a pending announcement on commercial crew. One of my bosses is off doing the work for the 2nd iteration of commercial cargo. So to say that anything's coming down would have to await, I'd say, the next iteration of contracting to say that it's coming down. But that's one of the intents of using the commercial side of things, is because they don't require themselves to adhere to the 40 years of bureaucracy that we've set up for ourselves.
Isn't that next round of contracts today?
It might be. I haven't seen whether they're going to announce you're talking commercial crew? Okay. For crew. So that's the crew side. There's another effort to do the extension of the SpaceX and orbital aspect, the commercial cargo side, that is not limited to those two to propose. And so we'll wait and see what the answers to that is. I think the RFI was about to go out, or the RFP was about to go out soon. Well, thanks a lot for coming, guys.